Hi all, thank you very much for being with us also today. It's a pleasure for me to introduce Professor Scalas, who's going to carry on with this cycle of mini lectures. Enrico, to you.
Thank you very much. So again, hopefully there are interruptions in my audio and you can, you will be able to hear me. If not, just let me know, and hopefully it is just lasting for a few seconds. And I will start sharing the screen while people are still coming, I see. So share, and we go to the fourth part of the presentation. So I should be able to put it full screen. And yes, today and tomorrow, it will the lectures will be really devoted to the object of the main object of this series of lectures, namely continuous time random walks or compound renewal processes, depending on your discipline of origin. So let us start as usual with a definition of the process. Then we will explore some properties, and in particular, as I have done with random walks and with renewal processes, we will focus on the one point or one-dimensional distribution. So we will try to find out the probability density function, and if you like, also the cumulative probability distribution function for the continuous time random walk. And then I think the exercise in itself will be clear from the presentation. So let me go to point one, the definition. It's a lot of words here, but focus on equation one. So we have a sequence of independent and identically distributed random variables. This time we call them yi. And we want to build a new process from them. We start from summing them, but this time, instead of summing them for a known number of elements of the sequence, we are summing them using a random number of elements. And what random number? A random number given by the counting process coming from the renewal process that is underlying the definition. So we will have another sequence of random variables, independent and identically distributed, this time positive, with a meaning of inter-arrival times between events. Then, as we did this morning, we can define the epochs and the counting process, and then essentially we take a time change random walk with the time change given by the renewal process. Or if you prefer, we sum a random number of yi. In this definition, implicitly, x at time 0 is 0. And I have not written this explicitly, but I have done this here explicitly. And so this object we call continuous time random walk, also known as compound renewal process. By changing time in this way, we moved from a stochastic process in discrete time, the random walk, where here you would have subscript small n, to this process, which is instantaneous. Counting process is defined for every positive and real. And we are interested, as I mentioned, on the derivation of the one-point probability density function, which we will denote with this symbol of density of xt. And so t is a parameter here. And then we are interested in rescaling this probability density function and showing that this is the solution of the Cauchy problem for generalized diffusion equations. But today we will focus on the diffusion equation itself. So we will make the connection between this kind of continuous time random walks and the diffusion equation after rescaling the random variables appropriately. What's next? Simulation, and actually we will focus now on the simulation. It is very easy to simulate a continuous time random walk. You just generate a finite sequence of inter-arrival times, so positive random variables with the meaning of inter-arrival times, and then from their cumulative sum, you have the epochs, so the instants at which events occur. And then you can simulate a finite sequence of jumps or steps. And then their cumulative sum gives the position of the random walk at step tn. Then you just plot xn versus tn and you're done. And now we will implement or see an implementation of this algorithm directly on your screen. And if you wish to know the value of the continuous time random walk at a given time, you just stop the simulation where the sum of the ji's is greater than t. And you take the values for which the sum of the ji's is smaller than t. And so the normalized histogram of x at time t approximates the probability density function that we are looking for. That's all very nice. Let me stop sharing to see if you have any question related to the continuous time random walk. I don't see any raised hands or any comment. So I will go on sharing the screen. Move out of full screen with the PDF. And let's stay on the simulation. And let's go and see our so you should be now able to see on your screen the program I have written to simulate a continuous time random walk. This simulation is not incredibly general. It works pretty well for continuous time random walks with finite mean, because you can control certain variables. If you want to use a program like this one for infinite means, you would have to modify it a bit. And I will tell you more as we are going on. Okay. So what we have here is setting the time at which we want to plot the histogram. I write here solution because this is a solution to generalized relaxation diffusion equation, but it is a density. Yes, so yes, I see here comment in the chat. Yes, I can remind the meaning of n of t. It is enough to go back to the presentation and to the presentation of this morning. There is already an answer which is correct, the number of events or arrival by time t. It is exactly like that, but I would like to give you more quantitative representation. I will not make it full screen, but a bit larger. And then remember, the meaning of the Tn is the sum from 1 to n of ji. And the meaning of nt is the maximum of the n such that Tn is smaller or equal than t. And this is counting the number of events between time 0, assumed to be as a renewal point, and time t, excluding the renewal point in 0. Yes, so this is counting the number of arrival between 0 and t. Okay, so the simulation, we set a number of iterations which will give us the sample size of xt. Then we define the vector of positions at time t, which is in this case 10. 10 is in arbitrary units, but then for physical processes, you might have to add a unit of time, and this unit of time depends on the specificity of your process. If you are interested, we can go into these details by separate discussion. And in fact, you are welcome. I will put this in the presentation also tomorrow. But because, of course, you are following so many courses now, and so, of course, many of you will be interested more in one topic than another one, etc., etc. But the idea of the summer school is to give you an overview of research in very different fields. You can always contact me in the next days using my email address. I will put the email address in the chat and then also in the presentation tomorrow. Now, we have defined the main variables. Then we start a loop. So the syntax of the loop in R is as follows. You use for. Then there is an index which is increasing. In this case, the index moves from 1 to the number of iterations. Then you open the curly brackets and you close them at the end of the loop. So this would be the end of the for loop. And this for loop, in more generality, can become a while loop if you want to use random variables with infinite mean defining the counting process. Now, what you are doing, you are generating many values of x of t. And this is time consuming because you have to simulate your process many times up to time t. How many times? 100,000 times. You will see that it takes a bit for the program to run. And because we are using a Bible distribution for the waiting time, 30 intervals are essentially always enough to overcome time equal to 10, because the mean of the variable is known. So you can take here a number which is larger than needed, and then you will always overcome the point equal to 10 by summing these. But what is the variable? Yeah, I have used the Wikipedia page, and this is the probability density function of a vibration. You see, this is a positive random variable, and probability density function.
Enrico, you have gone a little bit soft for quite a long time now. Some 30 seconds.
We're not. What about now? Can you hear
Now
me better?
it's fine. Yeah, now it's fine.
So, well, can you tell me if I was still on the program when I was not very well,
Well,
you could not hear me well? I was still describing the program.
I think you just landed on the Wikipedia page.
Okay, that's very good. So the Wikipedia page is just to illustrate the variable distribution and its parameters, where you have the probability density function here. You see, it's similar to the gamma distribution, and with some values of the parameters, you would, if I am not wrong, so the parameters are lambda and k, you would get the exponential distribution. And I can see here a question. Okay. That the microphone sound is not clear, so we knew that, and I will start sharing again. This is a non-exponential waiting time. So even if the mean is finite, and it is given by this formula here, where gamma is the gamma function, even if the mean is finite, you have a situation which process is no longer Markovian. It's a semi-Markov process technically. I will not go into these details, but it is no longer Markovian. And here you can insert really your favorite distribution. Well, by favorite, I mean the one you need for your specific application. Similarly for the jump. Random variables distributed according to the variable distribution, and here I am generating 30 normally distributed random variables, and this R norm is giving me the standard normal distribution with mean 1 and variance, mean 0, sorry, and variance 1. Then we set the initial condition for the epochs, t0 equal to 0, and the initial conditions for the positions, x0 equal to 0. I mean, this can be changed. You could even have an initial condition which is random, but let us not complicate our life, and let us start from 0 at time 0. Now, with the cumulative sum, you find the Tn's. So time is giving us the Tn's, and x is giving us the cumulative sum of the jumps. By using the C command, we add the 0 at the beginning. So here I could also put 0 here. You do the same with x. And then I think this particular command for the number of events is not activated in this program. Let me check, but I cannot see any calculation of the number of events up to time t. No, yes. no. It is computed here. Yes. So it is. Well, no. This is not really active. So I think I can safely comment this. And then here I am putting on the vector xt. So I could also comment this here. And here what I am doing, I am putting in xt the value that I obtain after checking all the values that are below time t. So in particular x of index, this is the maximum of all the indices such that time is smaller than 10. And to be fair, this is correct. So sorry. The index itself is the number of jumps. So, I mean, we don't need it for this presentation, but we are computing it correctly. And x of index is exactly x of t. So in this particular logic of the program, you can find other ones, or you can define other ones. And then let us see what happens. And we can also plot the last of these we can also plot the last of these random walks. Okay. I think we can stop before the plot, and I am putting here my email address. Oops. So that if you need to contact me and discuss something in the next days, you can do that. It's still running. It is a very long simulation indeed. You are generating sort of 100,000 samples of x of t, of x of 10 actually. And also there is in the background, there is our connection program, which is stealing resources. Okay, let me share the screen again. And so now, if everything went well, I can plot both the random walk and not only the random walk, but also the values at which you have jumps. Okay, so you see it here. What do you see here is on the y-axis is the position. So you start at 0 at time 0, then you jump somewhere, you jump again and again, etc. Sometimes you see these intervals are quite small, so you cannot appreciate. There are also superpositions of these. So when the random walk is here, it stays here for a random time, and then it jumps to a new position, stays at a random time, jumps to a new position, stays at a random time, which is quite small, jumping to a new position, etc. We are interested in the position at 10. So this last position at 10 would be at a value which is sort of 1.8 or 1.9, and we should have it in the vector xt, and then of course the random walk goes on. So this is not, it is a working code, but it is not a very efficient code. With a while you would stop here, and then your program would be faster. But to be fair, you see it lasted only, it was running only for a few seconds, maybe 10 or 15 seconds. And we can now plot the histogram of xt. Remember, in xt, we store the value of x at time 10. And maybe we say that we want 300 beans. And here is the result. So this is not a probability plot, but I can always write here something like that. I don't remember always this. Let's try like that. Yeah, it's working, and let's see. And now you see that if you integrate this object from minus infinity to plus infinity, or from one part to the larger part that you have, and then you take into account the size of the bean, you get essentially a 1. And now there is something interesting here. This huge peak in 0. And let me stop sharing. And let me ask you, do you think this huge peak in 0 is an error, or is it there for some specific reason? Remember that at time 0, we were starting at 0. No, it is not because of floating point arithmetic. No. It is really, it is correct. So the distribution of the random walk, you will see in a few minutes, that it is this distribution is singular in the origin. And it has a term which is Dirac delta that multiplies the survivor function for the renewal process. And so this is, of course, you cannot plot really a delta function, but still the histogram is recording a huge peak in the origin. And if you are integrating this, or you are computing the cumulative distribution function of x of 10, you will find a jump in 0. So that's singularity. While you are rescaling these variables, you will see that this singularity will disappear somehow. But
Enrico, we are probably missing an important part of your point, as we have lost from when you say
Yes.
when we can rescale these variables.
Yes. So what I wanted to say is that essentially.
Sorry, we still can't hear you.
And can you hear me now?
Not working yet. We see you clearly. We can't hear you.
Not clearly. Yes. So what about now? Still a problem? Maybe I could apply the first law of computer science and leave and come back. Can you hear me again?
Okay, sorry, it was my problem. Sorry. It appears that it was my problem. Sorry about that.
Ah, okay, okay. So it was not.
Thanks to Jamie, who was commented in the chat.
Thank you very much. Yes, so, sorry. Yes, yes. Yeah, I mean, I was just telling that this singularity is represented by this peak in 0, which is actually correct, and it gives you the correct mass in 0. But of course, this would be a delta function, essentially, so corresponding to really to a jump in 0. And now we will see it better. Yes, so I'm going back to the presentation. And this one is the presentation. And essentially, in this program, what we have done, the main step is to simulate the sequence of the J's and the sequence of the Y's, even if we change the name to the random variables, and then integrating them in order to get x of t, and then an approximation to this probability density function. Let me try to go full screen. To see my screen. On the simulation. So indeed, the one-point distribution is very easy to compute, and it can be derived by elementary probabilistic considerations. In particular, equation 2, what is telling me is the following. Remember the formula number 1. You have a random sum of random variables with this nt, which is completely decoupled or independent of the yi's. So the time randomness is totally decoupled, independent from the space randomness. For this reason, if you remember the presentation on random walks, the cumulative distribution of a random walk with n jumps would be the n-fold convolution of the cumulative distribution function of the single jump. But now you can go, you can have between 0 and time 0 and time t, you can have 0 jumps, 1 jump, 2 jumps, 3 jumps, etc., etc., etc. All these events are mutually exclusive. So you cannot have at the same time 1 jump and 5 jumps. Yes, so you are either you have 1 jump or 5 jumps. So they are mutually exclusive, and they are also exhaustive. So they cover all the possibilities. So you either have 0 jumps between zt, either have 1 jump between 0 and t, or 2 jumps, or 3 jumps, or 4 jumps, and so on. Okay. So you multiply this by the probability of nt, and you have the probability of going to x with n jumps. And you sum over all the possible n, and you have the probability of having the variable xt smaller or equal than x. Now you have here a convergent series which is made up of positive terms. You take the derivative, you can make take the derivative with respect to x of this function. This is not depending on x, this is depending on x, so it is just the density function of going up to position x in n jumps, and here it is. Yes, so you take the derivative of this, the derivative is this one. So you have very easily, by purely probabilistic considerations, the solution to the problem of finding the probability density function, where you have used essentially the fact that there is independence between the space jumps and the time structure of the process, so that they decouple and the probabilities multiply, and that's what is written here in equations 2 and 3. So these are consequences of the axiom of the third axiom of Kolmogorov, the axiom of infinite additivity. So if you are like Definetti and you do not believe in infinite additivity, you will not be able to write this equation here, but you can always stop at a finite step and still this equation will be fine. Now, suppose you want to take the Fourier Laplace transform of both sides of equation 3. So you take the Fourier Laplace transform here and the Fourier Laplace transform here. Now, the Fourier transform is acting on x, the Laplace transform is acting on t. And so you see here you have an n-fold convolution, which becomes a power of n. And here you have the Laplace transform of the counting distribution. Remember the result of this morning, that this is given by the Laplace transform of the survivor function for the single interval multiplied by the power n of the density Laplace transform for the single interval. Put this into this equation here, remembering that these objects have absolute values smaller than 1. You can sum this series, it's a geometric series, and get to equation 4. As we were doing this morning, you multiply this 1 minus f tilde j multiplied by f hat y1 on this side, and you end up with this Markov renewal equation, or semi-Markov renewal equation number 5, where you see clearly the emergence of the singularity in the origin. It is embedded in this equation, but you could see it also here, because the zero-fold convolution is by construction a delta function, and here the probability of having n events, 0 events time t is just the survivor function. So the first term of this sum is exactly this one. I mean, I'm putting this equation just as a curiosity. What you find a lot in the applied literature is equation 4, which is also known as Montral-Weiss equation for continuous time random walks. It was introduced by Montral and Weiss in a paper in the Journal of Mathematical Physics in the early 1960s, 1963, if I remember correctly. Okay, now let us consider a special process in which we want to apply equation 3, and we assume that these variables ji are exponentially distributed with parameter lambda, and the jumps yi are normally distributed with parameters mu equal to 0 and sigma square, where sigma square is the variance of the normal distribution. Now, we still have a step here, nth convolution of the normal distribution. And what is the sum of, what is the sigma of, what is the sigma of n independent and identically distributed random variables? Sigma square is n times the sigma of the individual jump. But moreover, there is something more. You can try it explicitly by computing the convolution for two Gaussian random variables with the same distribution. The normal distribution is stable, so it has the same shape. So you just plug in the variance, which is n times the variance of the single jump, and you have your n-fold convolution here. So this is the solution to the problem of finding the probability density function p of xt for any t in the case in which you have Poisson and normal. And if you have we will see tomorrow the Mittag-Leffler distribution. Here, you will have another expression which is giving you the probability of the counting process. Very well, which leads us to this calculation of the scaling limit. Before going to the scaling, any questions so far? I was running a bit for the distribution of the sum of Gaussian random variables, but it is a well-known fact, maybe you have even seen it in your lectures, that if you sum n identically distributed random variables that are normally distributed, the sum is still normal, and the mean is n times the original mean, in this case n times 0, and the variance is n times the original variance. This is not true for all distributions. It is a peculiarity of the so-called stable distributions, and the Gaussian is one of them. These stable distributions play an important role in the central limit theorem because they appear as a fixed point and as attractors in central limit theorem. And in particular, it explains why the Gaussian or normal distribution is the limiting distribution for the standard central limit theorem. Very good. So let me share the screen again. I think I still have 4 minutes to illustrate this limit. Using the simulation. So let me remove this picture. Let me go to this program, which I will now modify a bit by changing the simulation. Instead of considering 10,000 iterations, let us consider just 10 iterations. And instead of taking 30 samples, okay, let's start with 30 samples and rerun the program. We are just now using the program to plot the random walk. Yeah, you have this nice random walk here. What happens if I am increasing here the number of samples, maybe 300 samples? Look, the behavior is a bit different now. You still see the plateaus, but you see that there is, of course, the time is going larger and larger, but it is like seeing this random walk from a distance. We can go on. Maybe we had 3,000 samples here, and maybe we do not put the points here any longer because it's not really necessary. Look at it. So you still see that there are some plateaus here, but this object here is becoming closer and closer when you plot it to which process that we were discussing. In your opinion, we have a convergence to which process here? Any idea? Let me share the screen again. And let's put here 30,000 samples. What are you observing here? Let me run it another time. Don't be shy, and if you are shy, just share your ideas in the chat. Any idea on what process are we approximated? Yes, Jack, it is really Brownian motion. So this is a visual illustration of what I was telling you this morning, functional convergence of this random process to Brownian motion. So here we have that the time intervals are distributed according to the Weibel distribution with the finite mean, and the jumps are already normal. So they have finite variance in particular. All the moments are finite, but in particular the variance is finite. And you can really prove a functional limit theorem showing that if you perform a rescaling appropriately, you get in the limit Brownian motion. And if you fix the time, what we will see tomorrow, the random variable is distributed according to a standard normal. But I will stop here for today, and tomorrow we will go back to this transparency. Let me share the screen once more. Illustrating the central limit theorem for this process. And then we will put this in connection to differential equations and then pseudo-differential equations. And then we will conclude. I stop sharing, and I am waiting for your comments or questions. Please, Biagio.
Yeah, so thank you very much, Enrico. So we close officially the session, the lecture at least, and we will ask some questions to Enrico. So let's thank Enrico and let's stop the recording.